Hi, I'm Guoxi from Kyoto University. I'm going to present our paper on modeling long-term user engagement from stochastic feedback. This is a joint work with Xingyao and Xuanji Xiao. The background of this paper is to optimize long-term user engagement for feeds. Here is an example for feeds. I'm watching a video for a panda named Hua. I could scroll down for some related videos, such as videos for other pandas and animals. In the meantime, YouTube can display some advertisement to me. As designers, we want to optimize the user engagement for feed, which is the amount of time users spend on the platform. The reason is that an increase in user engagement can lead to an increase in active users, and also as many platforms display advertisements to users, more user engagement also lead to increase in revenue. In this study, we use reinforcement learning to optimize user engagement for feeds. To explain the motivation, let's illustrate feeds using this timeline. Let's use A for items and R for feedback of items. At step 1, the platform recommends a video for Hua and her keeper 10. I'm quite happy with this recommendation and gives a positive feedback. Then, the platform recommends another video for Hua, but actually I have seen this video before, so I'm not happy with it. At step 3, the platform gives me a video for Hua and her dead nanny. This appears to be a new video, so I'm happy with this video. As you can see, for feed, users interact with an agent continuously. To optimize user engagement, we need to optimize the sum of feedback during the entire process, that is, the sum of R. And this is exactly what RL can do. This paper addressed the computational cost of reinforcement learning for recommender system. To understand why the cost can be an issue, let's first briefly review the dequeuing algorithm. Let's use stay_as to represent the combination of user information, context information, and historical information. Then, this algorithm learns a function QSA to estimate the gamma discounted sum of rewards, where gamma is a hyperparameter. We can use QSA as a ranker, since larger values indicate more item consumption. To train QSA, we will assign the reward RSA and the maximum Q value at next state. S prime is this next state of S, and the maximum is taken over actions at S prime. As you can see, when training a dequeuing agent, we need to compute a maximum operation over candidate items. This operation incurs a huge overhead, as we need to store hundreds of candidate items for each sample. The second challenge is the randomness in feedback. Let's assume we have the same features for the blue user and orange user, so we will recommend the same items to them. Here, as they might have different interests, they will give us different feedback. Note that what appears to be the agent is that the rewards for the same users and items become random. What's more challenging is that the randomness accumulates when we optimize the sum of rewards. Our solution are twofold. We propose to learn the Q function of the production system that generates training data. As the production system is often highly optimized, we assume it can occasionally select items leading to more user engagement. Through learning the Q function of the production system, we are essentially mining the correlation between items and user engagement. The benefit is that we no longer need to compute the maximum over candidate items, so we do not need to store the candidate items. Meanwhile, we propose to model the distribution over the sum of rewards to handle its randomness. We address two types of randomness, the randomness in reward and the randomness in users' living behaviors. The idea is to regard the sum of rewards as a random variable and model its distribution. To this end, we use distributional reinforcement learning. You can check our paper for details. We evaluate the proposed method using online A/B test on an industrial short video recommendation service. The test was carried out for a week, and we measured the improvement on the production system after deploying some method. we consider two baselines. FD stands for fully deterministic, and it does not consider any randomness. RR means random reward, so it overlooks the randomness in users' living behaviors. The proposed method considers both randomness in reward and in user living behaviors. We compare algorithms for a variety of metrics. For example, VV means the number of video views, and DUR means the amount of time users spend on the platform. The numbers in parentheses are p-values. As you can see, FD couldn't significantly improve any metrics. RR can improve VV, CTR, and CVR, which means modeling randomness in reward is beneficial for improving user engagement. The proposed method outperforms RR for both VV and duration. This confirms the efficacy for modeling users' living behaviors. An increase in VV and DUR means users tend to watch more videos on the platform, and this implies they are more satisfied with our recommendation. Therefore, we confirm that the proposed method can significantly improve the user engagement for recommender systems. So in summary, in this paper we propose a new method for improving user engagement of recommender system. In specific, we address the efficiency issue of existing work and model the randomness in user feedback and living behaviors. We verify the efficacy of our proposed method using an online A/B test. Thank you.